So today we're going to discuss about tokenization. Now, tokenization may seem like a very trivial subject, but we'll try to establish why it is very important for all of you senior managers and executives to understand about it. Now, there are very critical organizational decisions which are based on this. Now, all I will discuss in these sessions are based on the research what I'm doing. I will provide you proof of everything as much as possible. Whatever I say, I will try to provide you with proof of that based on the experiments which I'm conducting. And I'll be sharing this slide deck with all of you. So there's no need to take notes unless you feel otherwise. So let's get started. So first thing what you need to understand is why do we need to understand about tokenization? Seems like a very trivial subject. Tokenization, you understand, is that we need to break the text into small segments. We will see different ways of doing it, but primarily you understand that what you understand through any NLP sessions you may have attended or whatever NLP readings you may have done. We basically break it up into words, like we find the location of the spaces or any sentence separating or word separating characters like a comma or a full stop or exclamation and things like that, and we break it up into words. Now, that's normally what we understand, but actually tokenization is quite more intense. It's not so simple, actually. Now, by breaking down into these tokens, you must understand that any kind of a LLM, when you're dealing with it, now LLM doesn't talk to you through words. It talks to you through tokens. So what happens is that when it is talking to you through tokens, what it is doing two things, actually. When you're writing something to the LLM, and now the LLM basically tries to understand whatever you've written by breaking down the input into tokens. And then after it breaks the input into tokens and understands, then it charges you based on number of tokens it took to break it down to understand the whole text matter, whatever you submitted, right? Not only text, we will discuss about text right now. Later on, we will also discuss about images or videos and things like that. But everything, ultimately, what happens is that whatever input you give it, it breaks it down into tokens. And then after breaking down into tokens, every LLM has its own strategy. And we will discuss about the different strategies which every LLM utilizes. And then after breaking them down into tokens, basically it counts how many tokens it will break it down. It needed to break it down into, and then what do you call? Then it charges you based on the number of input tokens, whatever you entered, and it had to break it down into. Normally the cost is around about, like OpenAI, ChatGPT charges you $3 for every 1 million tokens, whatever you interact with. Now the tokens not only include the input tokens, it also includes the output tokens. Output tokens are when it starts generating matter for you. Again, the matter what it generates is based on number of tokens it utilizes to generate the matter. Now, so it counts the total number of input tokens and total number of output tokens, and then it says, okay, fine, for this particular interaction, the charge on you is so and so. Okay, so that's how it goes. Now, we will also see that the input tokens are charged less and the output tokens are charged more. Normally, the output tokens are charged about 5 times more than the input tokens. So, what do you call? Because there are, you will understand that later on that the amount of processing required to generate the output tokens is much higher as compared to what it takes to generate the input tokens. So ultimately, the thing is that supposing like ChatGPT is charging you $3 per 1 million tokens. So if your ChatGPT is not doing the tokenization in an efficient manner, you can end up spending more. So you should know whether you should use ChatGPT or you should use Claude or Gemini, because their tokenization mechanisms can be much more efficient. Now this problem actually explodes. It is not just about interacting through the through the UI or GUI. It's also like you'll be at the enterprise level, you'll be writing programs where you will use the ChatGPT API or Gemini API or any other LLM's API, and you'll be giving instructions through the API, and then the API will take it to the ChatGPT engine or whatever LLM's engine, and then it will understand the input and then generate the output and give it back to your program. And then your program has to output the matter based on whatever the interaction happened with the LLM's engine. Now this whole process again, it calculates the total number of tokens involved, both input side and the output side, and then it calculates how much to charge you. So you'll get your API charges based on the interaction per interaction basis. Now here again, it becomes very critical for any kind of a CIO or any kind of artificial intelligence officer understand how much cost I'm going to have when I'm going to be making Gen AI systems or LLM based systems. So these are very critical decisions which you have to make. Now, while it seems very simple, like, I break it down into words and then I read just about words and then, but if you break it down into words, what happens is that, okay, fine, you have low number of tokens, relatively low number of tokens, but we will see later that you end up having a huge vocabulary because there'll be many different words in the whole corpus, in the whole input what you provide or the output it has to provide, and that will make the vocabulary quite high. And then the vocabulary, when it increases the processing cost and all the kind of stuff. But in general, word level tokenization produces lower amount of memory utilization, and trading cost is cheaper. On the other end, if I don't do it in a word level, but I consider every character as a token, then my vocabulary is very small because the characters can only be the ASCII characters. So there will be a maximum 256 number of items in my vocabulary. But what will happen is that the sequences will come. I'll show this in practice later on. So there, the memory utilization, etc., becomes very high. So there's a balancing which you have to do. So every time you are utilizing more resources, the LLM engine will charge you more for that. So you'll have to be conscious about that. So now there are many techniques which we'll not discuss today. I'm just introducing them to you. Like what I can do is that in order to reduce my cost, what I can do is that when I'm making a system, I can create a system such that I put some part of my regular instructions into a cache. We call this the prompt caching. So I put in the memory permanently, and then I apply my other queries. So when it is processing the queries, it will process these queries every time I put it. But this part is resident in the memory, so it will keep on taking inputs from this after processing it only once. And by doing this, by doing this prompt caching, I can reduce the amount of time I require to process my inputs and produce output. Now, this solves the latency problem. That is, I will require less amount of time to generate output from the LLM. But 1 minute, okay. On the other hand, what happens is that if I keep utilizing my LLM at regular hours, it can cost me a huge amount of money. So what I can do is that I can create batches of my prompts and I can feed them all at once in a single batch at maybe off hours. 1 minute, please mute yourself. Thank you. So at off hours, and then that way I can reduce my cost. With nearly 50% reduction in cost, I can achieve through this. So this is, I've tried to introduce you why you require to know about tokenization. What do you feel convinced with whatever we discussed so far? Do you have any questions? Yes, Sandeep.
So Partha, thank you. One question in this batching versus individual, the background processing for that particular prompt to generate the output, wouldn't that be same? So why would there be difference between batching versus individual?
No, if I do batching, the thing is that I can find out what is the off hours for a LLM, because LLM is something which is operating. It also has got peak hours and off hours and things like that. So the pricing differs based on that when the LLM is heavily utilized and when it is low utilization. So if I can figure that out, and if I can submit my batches during the off hours, I incur less cost.
It's just like cloud usage that you optimize.
Yeah.
Right? Okay. Thank you.
Any other questions at this stage? Okay, I guess no questions. If you have any questions, please ask. I'll try to answer as much as possible. Okay, now let's move forward. So now we've established why we need to know about tokenization, so you understand that it is a very important subject. Now then let's see what actually the tokenization whole concept actually comes from a very old technique, which is the data compression. Data compression, which we used to do. Data compression, it has been invented very long time back, ever since 1990s. We had this algorithm called Huffman algorithm, which is a very powerful algorithm. So now the whole concept of tokenization basically came from that. And why we are discussing so much about tokenization is basically because how much we can compress the matter such that the machine understands our semantics the best, and it is able to answer back in the best possible manner. So I will take a pause here, and I will show you what is this Hoffman mechanism all about, so you have a better understanding. And then we will see what concepts we can derive from it. So let's say, for example, I take a very simple example. Let's say I have a text here called India is great. So let's say India is great. So now the thing is that supposing I have to compress this, can you suggest any compression mechanism which can compress this text? Normally what I will require 1 byte per character, right? So I have 5 here, 6, 7, 8, 9 plus 5, 14. So I will require 14 bytes to store this. So do you have any idea how I can store it in less than 14 bytes? Anyone? Okay. Sorry. I'm tired. Okay. So now take for example, a very simple technique is like this. See, I require 8 bits or 1 byte to represent one character, right? So I require 1, 2, 3, 4, 5, 6, 7, 8. Okay, I can't jump. So I require 8 characters to store a byte. Now, supposing my text, whatever I input, only contains alphabets and numbers and punctuation marks, then I know that all of these things, all of these characters are within ASCII character 32 to ASCII character 128, right? So if I use only alphabets, numbers, punctuation, space, uh, and these characters, so I know that all my characters are between ASCII character 30 to 128. That means to say, to represent any kind of text like this, I require only 7 bits. Correct? You can tell me whether you agree or disagree, right? At least, so I know that you're following me. So I would normally take 8 bits to represent a character, but I see that all my text that I have, I can represent within 7 bits. So what can I do? Can someone tell me? So I can knock off the first bit from every character. So then I will be left with only 7 bits per character. And what I can do is that I can, oh, come on. Then I can do this 1, 2, 3, 4, 5, 6, 7. So then I take this second bit, put it in the first place, take the next one, put it in the second place. Like this, I can take these 7 bits from here and put it in this 7 bits. So that I have 7 bits here. This is 0, 1, 2, 3, 4, 5, 6, 7. Now I've taken this. This is now 0, 1, 2, 3, 4, 5, 6. So I've taken 7 bits. I have converted a 8-bit character into 7 bits. So I have now 1 remaining bit remaining. Then I take my next character, that is 1, 2, 3, 4, 5, 6, 7, 8. This is the next byte. That is, this was I. Now this is N. Again, I do the same thing. I knock off the most significant bit and take this whole stuff and put it here. So one bit comes here, and the next byte, that is 1, 2, 3, 4, 5, 6, 7, 8. So I have the next byte. On this next byte, I take the up to the 6th. So I can pack it like this. So you see that what I'm doing is that by doing this, I'm doing a compression. How much compression do I achieve? Anyone can tell me? Come on.
1 by 8.
1 by 8, correct. I achieve 12.5% compression. Right? Now when I receive this text at the other end, then what I should do? I should take the 7 bits together. I should take these 7 bits together and then add a MSP of 0. I do this. Then again, I take the next 7 bits together. I take this, add a MSP of 0. Then I will get a byte back. So this way I can achieve compression and I can decompress this compression. But nevertheless, you notice that this was, okay, fine. I had to understand the hidden language that I require to take out the first bit while compressing and I require to put back the first bit while decompressing. It's okay. It's a agreement which I can make. But then this was not very efficient because I'm only achieving 12.5% compression. Let's take a slightly more complicated mechanism. Supposing I take this text, India is great only, and I do the frequency count of this. So how many times will I appear in this text?
2 times.
3 times.
3 times.
3 times.
3 times. Right. And then N, 1 time. 1 time.
1 time.
I have already taken I, so I now next take A. A is twice.
2 times.
Yeah. Then space, 2 times, right?
2 times.
Yeah. The I is taken, S is once.
1.
Space is taken, G is how many?
1.
R, 1.
1.
And
E1.
E1
T1.
and T1. So I've done my frequency count, right? After doing my frequency count, what I do is that I take the least frequencies and I make a node out of that. So here are my least frequencies, 1 and 1. I take this and I make a node out of it. And the frequency of this node becomes 1 plus 1, that is 2, right? Then I go and search for the next 2 lowest frequencies. So I find the lowest frequencies are here. So I make a node out of this. So this frequency at the node becomes 2. And then I take, okay, these 2 are also 1, 1. So I take these 2 and I make a node out of this. So this becomes 2. And then now I have again, okay, now this 1 is there and this 2 is there. So I make a node out of this. So 2 and 1 makes it 3. So this becomes a node. Now where is my least frequencies? So this is again a least frequency 2 and 2. So I make a node out of this. So this becomes 4, right? Where are my lowest frequencies? These 2 also have a lowest frequency now. So I make this as 4, right? Now what do I have left? 3 and 3. So 3, I take this and I take this 3 and this becomes a node of 6. Now what do I have? 4 and 4. So I take this 4 and I take this 4 and I make a node out of it. This is 8. And then I take this 6 and 8 and this becomes 14. Okay, so what I have done is that I have created something which is, this is known as the Huffman tree. Okay, this is known as the Huffman tree. Let's see how to utilize this tree for compression, right? So now what I do is that on this nodes which I created, I'll consistently put a 0 on one side and a 1 on one side. So I put a 0 on the right hand side and a 1 on the left hand side. So I put a 0 here and a 1 here. I put a 0 here and a 1 here. And I put a 0 here and a 1 here. And I put a 0 here and a 1 here. Then I put a 0 here and a 1 here, a 0 here and a 1 here. Right? So you have followed the strategy so far, right? No confusions? I hope, right? Okay. Now what I do is that I have to encode. So what I do is I take my, there's a 0 here and a 1 here. So I take I. Now I traverse from I to the root. This is the root. This is the root. So now you see here, if I have to go, I come here, this is 0. And then I come here, this is 0. And then I come here, this is 1. Am I doing it right? No, I'm not doing it right. This is 0 here. And then I come here, this is 0 here. So I becomes from, I will count from the root. So 0, 0. If I go this path, 0 and a 0, I get a I. So I's encoding becomes 0, 0. Okay. Then I take N. How do I reach N? This is 0, 0, 0, 1. Correct? Do you agree? So the coding becomes 1, 0, 0, 0. So this code becomes 1, 0, 0, 0. Then I come to D. So what is D's code? D is 1 here, 0 here, 0 here, 1 here. So it is 1, 0, 0, 1. So D is encoded as 1, 0, 0, 1. Okay, let me do a last one. I already know this is 0, 0. And A, let me do. I traverse from here. This is 1, then a 0 and a 1. So 1, 0, 1. So A is 1, 0, 1. Now you see, when I'm going to write my output, I will write it as India. I will write it as 0, 0, 1, 0, 0, 0, then 1, 0, 0, 1, then 0, 0, and then 1, 0, 1. This is how many bytes? This is 1, 2, 3, 4, 5, 6, 7, 8. 1 byte here. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. So I still have one more bit left for making 2 bytes. So you see here, I have compressed from 5 bytes to 2 bytes. Less than 2 bytes, right? If I write the whole stuff, it will be much lesser. Anyway, you know how to do that. Now let's see whether you can decode it. So it says 0, 0. So I go to my tree here again. I need to have the tree. So I need to go to the tree here. I go to 0 and a 0 and I hit a leaf. So I know that this part is one symbol. So let me change the color. So I know that this part is a symbol. So I say this symbol is I. Then I again start 1, 1, 0, 0, 0. So I know that this is one more symbol and this is N. And this way I can carry on. So I'll do a last one. Come on. This is 1, 1, 0, then 0, then 1. So this is ending up here. So this is a D. So 1, 0, 0, 1 is D. So you got the idea how I can do the encoding and decoding? Did you get
Yes.
it? Does anyone have a question?
Sir, a question.
How? Yeah, I have a question, sir. How will I know that the node, that the leaf that is ending in 0, 0 is I? Like it may be anything depending on the token I gave, right, initially?
No, that's right. That's a good question, but you must raise your hand. Okay, I will wait for, who was that? Sandeep, you raised your hand, or who was that? I will answer.
My name is Srividya.
Yeah.
I will answer your question, but you must raise your hand. There was somebody who raised his hand. Let me answer his question.
Okay, I didn't know that. 1 minute. I don't know how to raise my.
Yeah, Sandeep, you had a question?
Yeah, it was same question. Like if we had a similar, like let's say after 0, 0, we had something else in the beginning. How would we know that we have to take first 2 or first 3 or 5? It can be anything.
Okay. Now look here. I have to have this tree, right? So now I take the first bit. I do not know where it will end. So I take the first bit. It says 0. So I go here. Then it says the next bit is also 0. So I go here. When I go here, I see that I've hit a leaf, right? And that leaf happens to be I. So I know that there is a character I found here. So this much is representing I. Okay. Now, your important question, what both of you have asked is, how do I know that what is the symbol? It could be anything. So what do I need? I need to store this complete frequency table in my memory or in whatever mechanism, so that I can recreate the tree which I utilized for compression while decompressing. Do you understand what I said?
Yeah, got it. Yeah.
Okay. So when I get my text, I create the frequency table. From the text, it is possible. Do you agree with that?
Yes.
Yes. After I create my frequency table, can I utilize my strategy to create the Huffman tree? That's possible.
Yes.
After I create my Huffman tree, is it possible for me to encode all these? Correct?
Yes.
That's also possible. After I do that, now I have completed my compression. I have sent this compressed text to another machine. Now what I should send? I should not just send the compressed text, but I should also add the frequency table along with it. This is the frequency table. Right? So actually I achieved a lot of compression, but by adding the frequency table, I have inflated my compressed data. Right? Only when I receive the compressed data along with the frequency table, I will take the frequency table and I will recreate my complete Huffman tree. And once I'm able to recreate it, then I'm able to decode this back into the normal bytes which I had encoded. Do you get the idea?
Yeah. But Partha, is it possible, let's say, it's not in this case, but let's say for something, it would have been 1010 as well. Is it possible?
Yeah,
Maybe we.
definitely it will be. Let's complete that.
But if that is the case, then how would we know it is A or that other character 1010?
Now let me complete this table. I did up to A, right? Now let me do for blank. Let's do it for the rest of the characters. Then your question will get answered. It's such a powerful technique that let's do it for blank. What is the code for blank? Blank is here 0, 1, 0. Right? So this is 0, 1 and 0. So this is 0, 1, 0. After a blank is S. S is what? S is 1, 1, 0. Correct? Did I do it right?
Yeah.
Yeah, 0, 1, 1. So 0, 1, 1. After S is G. G is 0. This is 0, 1. 0, 0, 1, 1. Well, that is 1, 1, 0, 0. 1, 1, 0, 0.
Partha, sorry, I think S is 110.
110. Why? S
1. That is 1.
I take it from the root, right? I will always take it from the root. So this is 0.
No, but the root,
1,
yeah, this is
1.
1. Yeah. Oh, you're taking from the root. Okay. Yeah. Sorry.
Okay. Okay. Now comes R. R is 1, 0, 1, 1. 1, 1, 0, 1. So 1, 1, 0, 1. And then E. E is 0, 1, 1, 1. 1, 1, 1, 0. So 1, oh. One, 1, 0. And last comes T. T is 1, 1, 1, 1. Now notice something here. I planted all the codes. Now do you see that every alphabet has got a different code? Are you able to see that?
Yes.
Right? Everything has got a different code. Correct? So when you are going to compress it and when you try to decompress, you will never find a situation where you will be having a duplicacy. It guarantees a unique code for every character. Anyone has a question here or any doubt here? Yes, Aditi.
Partha, I'm not sure if this case might happen, but let's say if it tries to read not 00, but let's say 0010, or can that kind of a case happen when it does not know that where to stop?
No, it will never be the case. I suggest, if you want to convince yourself, just try any random example. Any random example. Follow this technique which I told you. You will see that you will always get unique codes, and you will never be in a situation where you cannot find out which the character is.
And it will always trace it back to the root.
It will always trace it back to the root.
Okay, thanks.
Okay. Yes, Srividya.
If we are going to pass the frequency table along with the compressed node, how are we saving in this case?
That is the important. That is a very important question. Now, thing is that, you see, I achieved a lot by compressing the text here. But after compressing, I had to add the frequency table. And that actually made the entire, in this particular case, it made the entire load much larger than the input. Do you notice that? Like what Srividya is pointing out. So I'm not actually achieving compression. So I should be careful that I compress enough text so that I get the benefit of compression. Now by Huffman technique, I can achieve up to 72% compression. Okay, it's a huge amount of compression what I can achieve. But I should have sufficient amount of text, and the text should be such that the frequency table should not offset its compression value. But now we come to a very important point. I will discuss that after taking Yogita's question. Yogita?
Yes, sir. My query was, right now we took a small sentence, India is great. But if we are considering something to translate like Mahabharat, old text, is the delimiter a full stop and we should create such trees for each sentence?
Not sentence, character by character. I'm doing it. Correct? I'm doing it character by character. What is this? This is a frequency table of the individual characters in my text.
Okay, so only 26 alphabets and a space, or other special characters?
Special characters can be numbers.
Okay. Right? ASCII set. Okay.
ASCII set, anything. It can have any symbols also. That's a 256 character. I can utilize the entire ASCII set of 256 symbols. But whatever, I will have the frequency table of the individual characters. And that frequency table, I should pack it along with it. Now, if I compress Mahabharat, I will have the frequency table, but I will have a huge text which will get compressed. So I can easily expect up to 60 to 75% of compression on that text.
Okay, got it. Is this true for other languages also? So Mandarin character set, will it exceed and give me the same ROI?
Yeah. Yes. It will give you. This is a very good technique.
Okay. Thank you, sir.
Yes, Vinod.
Wanted to know, it's like how is it used? Like, do you create the frequency table page by page, or for the entire document, even if it is a very large document?
For the entire document. I will create the frequency table for the entire document, and then I will form the tree and I will compress.
Okay, so it's that's the actual way it is implemented, is it? Yeah. It's instead of chunks.
Yeah.
Okay. Thanks.
If I do it in chunks, I have to store the frequency table multiple number of times, which will defeat the whole purpose of compression.
Yeah, that's why I asked, because when you can optimize the frequency only if you do it over larger. So I agree. Thanks.
Okay. Now we come to a very important point. That is, you notice here, what did I do? I compressed, which was my main purpose. But along with the compression, I stored my frequency table. Now, this is a concept which they have taken into LLMs also. In LLMs, what we do is that we will see how LLMs are encoded. But along with the encoding, LLMs have something known as the vocabulary table. Okay. So that is the vocab. Now, the LLMs, what they will do is that the vocabulary table is what the LLMs utilize to decode your tokens. because this contains the tokens. This contains tokens which the language stores in order to do the decoding. Now, this idea from compression they have taken into LLMs, where they have something known as a vocabulary table, and we will see in the subsequent classes and today also to some extent how the whole vocabulary table is utilized for decoding your text and generating new text or understanding your old text. Okay, so far we are good. Do you have any questions? Yes, Deva.
So Partha, when you said the vocab table is what is token, so my understanding, if I map this Hoffman technique, instead of the frequency of the characters, they are trying to create the frequency of the vocabularies that they have for the entire document, and then they use that for compression. Is that correct understanding?
It is partly correct. The thing is that I will keep the tokens for sure, but I do not require to store the frequency in the case of LLMs. Okay, we will see why it is not required, but I require the tokens, right?
Okay.
In fact, to be more clear, what I'll supposing my token is word called win. Supposing this is my token. So what I will store in my vocabulary is this token is actually the number 0156. This is what I will store in my vocabulary table. Okay. Why it is stored? Now you may ask the question why this is stored. So now we all know that machines cannot understand words. So it has to convert everything into numbers. So I've done the number conversion. So now I'm getting a sequence which has got a huge number of numbers inside it. And now I see that I find 0156 here. 0156. Now 0156 is either received during input or during output, whichever way, it doesn't matter. But moment I see 0156, I say that this maps to this vocabulary. That means to say this has to be win. Do you get it, Deva?
Yes, Partha, thank you.
But the idea is clear to all of you now?
So one question, is this
Yes.
the same across all the languages?
Yes, all LLMs. This is a mandatory requirement, this idea.
Okay, for any language, for example, Telugu, Tamil, Malayalam, any language?
Anything.
Okay, sure.
Okay. Yes, Eknath.
So, as our document is large enough, subsequently our frequency table also will be significantly larger. So do we have as I understand, this is currently in memory, but do we have some efficient mechanism to store frequency table for very large records or very large data sets?
No, see this Hoffman technique I programmed first time when I was somewhere around about 1999. Now that time, though we had primitive, primitive systems. The thing is that the only efficient mechanism, and I coded in C, only efficient mechanism is that I should load my frequency table into the RAM. Okay, I cannot have it in any kind of secondary storage or anything or virtual machine or anything like that. In fact, we didn't have cache memory in those days. If it was possible to have cache memory, I would have stored this in the cache memory. I have to have this in the RAM or cache memory primarily because if I don't do that, the whole processing of this entire decoding, encoding will become extremely slow. If I want efficiency of my data compression program, I require to have this entire stuff inside my RAM. In fact, not only the frequency table, I should have, after the frequency table, I should have the entire tree inside my RAM or the cache. Okay. And in LLM's case, you have to have the vocabulary inside the main memory or RAM. And that is the reason why we will discuss later what is the trade-off when we have a large vocabulary versus when we have a small vocabulary. So we will see the different techniques and then we will understand why it is so important to decide upon the right technique for tokenization. Eknath, does this answer your question?
Yes, sir, I got it. Thank you.
Okay. So now let's move forward. I have to keep tab on time also. Okay. Now you see that the first thing we did with tokenization was that we did a word level tokenization. Word level tokenization means what? Supposing I have the same sentence, India is great. So I will hunt for delimiters like this. Let's say this is the one, and this is a sentence. So I will hunt for the delimiters. I will look for a space. I will look for a space here. I will say that you are one word, you are one word, and you are one word. So then what I will do is that I will create a token out of this word. I will create a token out of this word. I will create a token out of this word. So maybe I will number it as 01, 02, 03. Right? Now this way what will happen is that there are two issues in this. One is that notice when your text is very large, your number of tokens will be very large. And I need to maintain a vocabulary inside my machine, which will be quite large. So I will have a large vocabulary. Even in spite of maintaining a very large vocabulary, what happens is that supposing I train a LLM and I have done a byte level tokenization, I've done a word level tokenization. Now I have a vocabulary which contains the words and the corresponding symbols. In this case, the vocabulary will contain India is 01, then is 02, and great is 03. So I will have a vocabulary table like this. Now what can happen is that I trained my LLM, which contains a large number of words and vocabulary and everything. Now, but then I input a new text in which I bring about a word, something like this. I input something like India wins. Now it found India in my vocabulary. It found it. It says, okay, fine, you're 01 token. Now it cannot find the word wins here, right? So what it will do is that it will mark this by some symbol like this as unknown, because it is out of its vocabulary. So this is a frequent problem which we have when we do word level tokenization. Now, what happens for a LLM's purpose is that as long as it has got these words within its vocabulary, it can make some meaning out of it. Not that it's understanding that India is a country. That happens through a different process. But right now, it knows that India is a word in my vocabulary, though it doesn't really know what really India is all about. It is whether it's a country, whether it's a fruit, whether it's a toy. It doesn't know anything. But still, it has got some kind of understanding of this. But when it comes to this unknown, it has no semantic meaning. So when I have large number of unknowns in my text, the understanding of the LLM, it drastically goes down. So this is Vinod.
I didn't understand what you mean by semantic, because in the frequency table you're just storing a sequence, right? Are you referring to the sequence as semantic?
Not semantic. Right now, I have not got any semantic meaning. Right now, I have only stored a token. This is not a frequency. This is a token number. Okay. This is a token number. This is just a token number. But understood. Then in the next session when we conduct, I will discuss the topic of word embedding. You can mark this. So next class we will discuss about word embedding. So in word embedding, what we will do is that we will use a neural network, and using the neural network, each word will get a semantic meaning, right? So right now I'm just preparing for that step, but next time when we have the class, we will discuss about word embedding, where I will teach the machine how to make meaning out of individual tokens, what it has extracted.
Okay, thank you.
Okay. Anyone has any questions so far? Are you understanding what we are discussing? Yes, Sandeep.
So continuing on this unknown thing, what happens with wins now then?
Yeah, it is a token, but since it is not in the vocabulary, it is marked as unknown. So it has got a generic meaning, which is something which does not really make any meaning for the LLM. It cannot make any. It cannot create any kind of meaning out of this. What to do with this particular word wins?
But isn't it true? Like, let's say, until it finishes all the vocabulary in the word, it will keep encountering with every interaction new word. So shouldn't this table be updated vocabulary once you
See, I will train my LLM once, right? Now, till my next round of training, I have to just keep on using that LLM.
Okay, got it. Okay.
Right. So if you have a lot of these out of vocabulary stuff, then your performance of the LLM will drastically reduce. Okay. Now to solve this problem, what we did was that, yes, Megha.
Partha sir, just a question. So in case, right, LLM, right, so if say a word is spelled wrongly, right, then obviously it will end up as an unknown, right? It will be an error.
Yes, it will end up as unknown if the word is spelled wrong. So for that, what we do is that, well, how to tackle that is that, normally when I'm training a LLM, before I do the token extraction, I will do a minimal pre-processing of the data. Okay. I will do some minimal pre-processing. In this pre-processing, I will try to remove as many number of possible such known problems, like you said, spelling mistakes and things like that, so that the corpus which goes into training the LLM is as clean as possible. You get it?
Yeah, I get it. Another question I have is, so say nowadays people use emojis, right, a lot. So say a colon and then bracket, right? So it's like a smiley. So how is that?
Yeah, the emoji also is a token.
So we are saying, so we have different, so basically these delimiters, right? These punctuation marks actually. So these punctuation marks would be, so a colon is just a colon. It's a separate thing. But then a colon which is followed by, say, a closed bracket, right? So it is a different thing. So we have these combinations of punctuations also marked as tokens.
Now see that in word level tokenization, what happens is that any kind of punctuation mark is treated as a separator of words. Okay. So I will show you the program also. You notice that these punctuation marks, they get separated out and they are no longer considered as a token. They are only considered as delimiter of words. That's another problem with this word level tokenization.
Okay, got it.
Okay. Yes, Sandeep.
So, Partha, to reduce the chances of this unknown, isn't it recommended then in the first go, let's say if I'm creating something for pharma, so pick up the encyclopedia of that particular topic and then feed into that, because that will make the vocabulary as exhaustive as possible?
Yes, we will come to that use case also. Right now, what we are discussing is a general purpose LLM. Okay. Now we will come to the use case like you pointed out. Like there are many use cases like this. Suppose, like, for example, I make a general purpose LLM, like you have ChatGPT or Gemini, for example. You try to apply ChatGPT or Gemini or Claude on a legal system. You will notice that you're getting horrible answers because they will not understand most of what those legal documents are talking about. Similarly, pharma, it will not understand most of what the pharma documents are talking about. So for those cases, we require to train a special purpose LLM specifically for that domain.
Okay.
Okay. Yes, Jacob.
So, Bhakta sir, a quick one. This table, right? The lookup table. If India is in quotes, will it be a different lookup?
No, in the word level tokenizer, it will not be a different lookup, because like I'm telling you, in word level tokenizer, what it does is that every special character which it thinks is a separator of word, it will remove that and consider only the word inside that.
Okay. So the quotes doesn't matter.
Quotes will not matter in the word level tokenizer, but it will matter in other tokenizer. I will show you that. Okay.
Yeah.
Megha, you have a further question?
Yeah. So one more question I had is, so we are creating tokens out of just words, but then sometimes a single word can have multiple meanings. So more context is needed, right, for the LLM to understand those words?
That will come when we discuss about word embedding. Right now, we only tokenize.
Okay, got it. Thank you.
You have to wait for the session on word embedding. Okay. Okay. So you saw that we have this tokenization technique. It is very widely utilized, but it has got a lot of problems. For example, ChatGPT utilizes this technique, right? So it has problems. Now, what was done instead of doing this is that I consider a vocabulary table to only contain the individual characters inside a text. Okay. So for the same example, I will have a vocabulary table as I is token 01, N is token 02, right? D is token 03, and so on. So in this case, how many maximum number of tokens can my vocabulary table have? Any idea?
All printable ASCIIs.
256.
Yeah.
So in this case, you saw that my vocabulary table can be quite large. But here, my vocabulary table is always very small. Right? Yes or no?
Yep.
Yes. Now, I'm tired of this Microsoft Word. I every day take classes in this. I'm always tired of this. Okay. Now look at this. In word level tokenization, when I tokenize this input, it becomes 01 in my current case, 02, 03. Correct? You guys agree with this? This is what the machine will see. Because I created this vocabulary, India is 01, is this 02, great is 03. So machine will only see this, right?
Yes.
Yes or no? Yes?
Yeah.
Yes.
Yeah, okay. Now look at this. I now consider that every single character is a token. So now I encode along, my vocabulary size is very small. But then I encode this. The same thing will become India is 01, I is 01, N is 02, D is 03, I is 01, and A is maybe 04. And you see that India itself has become such a long sequence now. Yes?
Yes.
Yes.
You see that my sequences are becoming longer with this character logic, character level logic, as compared to word level logic.
Correct.
Right. But then I will not have the problem of out of vocabulary. Do you agree with that?
Yes.
Yeah. I'm guaranteed that I will not be having out of vocabulary, but my sequences will become extremely large. Right. So this is the,
Yes.
I have a solution, but I have a bigger problem also. Okay. Now you must ask me the question, why am I talking about the sequence length and things like that? So while without getting into details of word embedding, now what I will do is that I will actually create out of these tokens, I will create vectors. Okay. I will create vectors. So people who have an understanding of word embedding will be able to catch it immediately, or others just wait for the next class and I will create vectors. Now, these vectors, these word embeddings, what I create, actually become my input to the neural network, which I will utilize for training my transformer. My transformer is what the LLM is all about. So I will have this as my input. So this is the input node. So I will have now look at this. Supposing my sequence length is large, then will my input length to the neural network be large or not?
Yeah, it will be large.
Yes, it will be large.
It will be large. See, if the input length is itself large, will there not be a tax on processing my neural network?
Yes.
Common sense, right?
Yes.
Mm-hmm.
Correct. Okay, then forget about this is something we'll discuss later. Then I have a neural network which is quite dense, or whatever I do with my neural network, I have this. Then I have further layers and I have all of these things. Now, ultimately, I come to my final layer. This is my neural network. Ultimately, I come to my final layer. Final layer will contain what? Final layer will contain a series of nodes, which is equivalent to how many numbers? Any guess?
256.
In the case of character, maximum it can be 256. Correct?
Yes.
And in the case of word level tokenizer, how much it can be?
It can be a huge number.
It can be a huge number because based on the vocabulary. Right. So now in character level tokenization, I will have a small output layer. And in case of word level tokenization, I will have a huge output layer. What is the impact of this? Impact is that what does a LLM do? LLM actually only guesses the next word, next token, not even word, the next token. LLM is not an intelligent machine which understands your language. No matter whatever it is, Chinese, Japanese, English, it doesn't understand anything. All it is doing is that it is trying to guess which is the next token to output. Now, to guess the next token to output, it will take all the possible tokens and give a probability that this can be the token. It will give a probability. This P1, P2, P3, etc. Now, if my output layer is small, this assignment of probabilities, which we know as the softmax function, softmax. Now, this process of assigning probabilities will be less computationally heavy. Do you agree with that?
Yes, sir.
And if this layer is very large, then the assignment of softmax will be very heavy.
Yes.
Agree, sir.
Agree?
Yep.
Okay. Now let's see. So now actually neither of these techniques are utilized by the modern LLMs. This was the time when LLM started. They tried these techniques. So what does the modern LLM do? Do you need a break before this? 2 minutes or 5 minutes?
Yes, sir.
Okay, let's take a break for 5 minutes.
Hello, sir. I have a general question related
Yeah.
to this session. So this session is part of some series, or this is some part of research work or anything?
It's part of a series. I'm conducting this series on LLM architecture. So I just started the process. So gradually I will take you down to the details of the LLM architecture.
Okay. So could I get like previous session or maybe slides?
No, this is the first session.
Okay, thank you.
Partha, I could not find the page. I was trying to find a place where all of the sessions that you're conducting are listed. Is there a page like this available?
Actually, I do not know. Because
I could not find that on LinkedIn at least.
No, on LinkedIn, see this, you can go under my page, events. So here all my sessions are recorded.
Oh, I see. Okay. Thanks.
Okay. Okay, let's get back. Now you saw that we had these two techniques, word level and character level, and there were some problems. So what ChatGPT or GPT OpenAI uses is that something known as a subword tokenization. In fact, their technique is specifically called BPE, Byte-Pair Encoding. Okay. So now the basic idea in Byte-Pair Encoding is that I have a vocabulary, a pre-built vocabulary will be there with the LLM. First of all, it will take a token. It will take what do you call it? First of all, Chat GPT or GPT model. It breaks it out into words. Okay, it uses what do you call word separators. It has a sophisticated word separator, and it will break it out into words. Now, if it finds the word is there in the vocabulary, it straight away takes the code and assigns it to it. Okay, that much part we have discussed previously already. Now, supposing it finds a word which is not in the vocabulary, then it will try to find what is the best way to represent this word. Okay, now you can see that it is able to break it out into like this, but let's understand how it does this breaking. Okay, so let's do that next. So now supposing I have a corpus, let's take a simple corpus in which I have the word low and it appears 12 times, and I have the word lowest and it appears 5 times. Take a simple corpus like this. What byte-pair encoding will do is that it will take two consecutive byte pairs, that is L and O. So it takes LO. How many times will LO appear in my corpus?
17 times.
17 times. 12 plus 5. Right. Then it will take OW. It also appears 17 times. Right. Then it takes WE and it appears how many times? 5
times.
Then it takes ES and it appears 5 times. And then it takes ST and it appears 5 times. So it has taken just 2 bytes at a time. Now it finds which are the most frequently occurring byte pairs. So here I have 2 cases where I have these byte pairs which are appearing most frequently. Right. Then what it will do is that it will say that, okay, fine, I will make a token out of LO. Let me call it token number T01. It will not be T01, it will be 0102. Just for representation of understanding, I'm doing this. And it will say I'll make a token out of this, that is T02. Right? Makes sense so far? Yes or no?
Yes.
Yes.
Okay. Now that it says that I have got a token called LO, let me try to combine the next byte also into this. So it will take another byte and it will say low is a token. And it appears how many times? 17 times. Right? And it sees that OW it cannot make any further. It remains OW only. And remaining are anyway less frequent, so it will not consider that. Now it says that I have got a meaningful token in LOW containing a existing byte pair. So let me make this into a permanent token. Okay. Let me make this into a permanent token. So it will now assign a fixed token number, let's say 2156 to this token, and it will say you are a token in my vocabulary. Okay. Then similarly, it will try to see, you got the idea how byte pair encoding is happening? Anyone has any question, doubt, observation?
Partha sir, I am not very clear. I didn't understand this last part.
You see, it has taken LO as frequently occurring, right? It assigned a token number. Let's say the token number is 5122. 512. And this is 513. Let me make it proper. That takes this byte pair. It has become a token, but to this token it takes the next byte also. What is the next byte? W. So now it has made a byte pair of LO and W. LO was 512 and W was a character, right? So now it sees that, oh, this LOW is occurring how many times?
12.
Come on. I'm
or
not even
17.
moving my mouse. It is appearing 17 times, right?
Yeah.
That is, in this particular corpus, this is the most frequently occurring token. So it is a greedy algorithm. Greedy means it sees that which is the most frequent. This is most frequent, so let's make a token out of it.
Okay.
Okay. If it makes a token out of it, now what happens? Oh, come on. So this I get as one token, 2156. Okay. And this becomes one token, 2156. And then what can happen in the worst case? The worst case, what can happen is that I can have 3 more tokens as E, S and T. Correct? This is the worst case possible. But if I have more text, it is quite possible that EST itself will become one token. Right? If EST becomes a token and goes into my vocabulary, then what will happen? Supposing I have the word best, what will GPT look at it as? It look at it as B plus EST. Got it?
Yeah, got it. Thank you.
Are you all clear about byte-pair encoding? Subword tokening? Yes, Vinod.
Here, why did you stop with 3 characters? I mean, is the token
No, this
size?
is my corpus.
Okay.
This is my corpus.
Okay, so the token size is not fixed.
Yeah.
It's based on the corpus. And what LLMs usually talk in terms of parameters? Is it same as
The
this?
parameter I will come to.
Okay, cool.
Tokens only determine the parameters, but I will come to that slightly later.
Okay.
Not today. Okay.
Okay.
But you understood what is subword tokenization, right?
Yeah.
Everyone, anyone has a question?
So if it had 3 words, let's say low, lowest, lower.
Okay. Lower. Let us do it for this. This appears, let's say, how many? This appears 3 times, let's say. Now you calculate. Again, I will get low appearing 20 times. Right? So it will make sense to make one token out of low. So it will have low. It will have low plus maybe EST. I do not know yet. Maybe EST. And it can have low plus maybe ER. Maybe. I do not know. This part I'm not certain from this, right? Yes, Vinod.
Will LOWE not be a token because it will appear 8 times?
Huh?
LOWE.
But that is less than LOW, right?
Okay. Okay. So maximum frequency.
Yeah. Greedy algorithm.
Okay. Got it. Thanks.
Vinod?
Yeah, got it, sir. Thanks.
Okay. Any other questions coming to your mind? Okay. To convince you guys, let me show you a demonstration. Okay. We may overshoot the session, but I will try to be on time. Let me see how far best I can do. Okay. This is the experiment which I'm doing on the complete works of Shakespeare. Now, let me just install some libraries. Okay, I'm downloading the Shakespeare's text here. So it has got around about 5.3 million characters. Okay. Now I'm doing a character level tokenizer. Okay. So character tokenizer I'm doing. So you see that it is reading every character and it is forming a token out of that. And then you see that it is, when I'm seeing the token IDs, it has got 888, 243, 45 and like this. These are the token IDs. And if I look at this, the actual text of these tokens, it is like this, start of the project. So let's just do that. It takes 888, right? That is start. That is the same character. It has done it 3 times. Notice very carefully that it has not considered any of the spaces as a token. Okay. See here. No, it has considered the spaces as a token. You see here, 2 is appearing for this token, 2 is appearing for this, and 2 is appearing for this, and so on. So character level tokenization, space is also a token, right? Now let's take a character like A. So it is the third. So 1, 2, 3, 25. A is 25. Do I have any other A? No, I took the wrong character. Let's take T. T is 44. And then T is again 44 here. And then this T is O space OF T. T is again 44 here. Do you get the idea? Any questions? All good?
Yeah.
Okay. Now let's take the word level tokenizer. So this one, what it will do is that it will split according to the words and then it will tokenize. So let's see how it does it. So here you see that it has considered every separator character as a token. Now in this case you see that it took star as a single token, but here it has taken it as a single token and it has created a separate token out of each of the stars. Then you see that it ignores all the spaces and it is only taken the words as a token. You notice that? Most significantly, this word and this word are 2 different tokens. Do you notice that?
Yeah.
It has no understanding of your language. Are you getting convinced as we are progressing?
Yes, sir.
Okay. Okay. Now let's take the third tokenizer what we discussed. That is the one which GPT uses, that is Byte-Pair Encoding. So let me run this. So now you see that in Byte-Pair Encoding, it has taken star as a single token. Okay. Then it takes space start as a single token. Space off as a single token. Like this it is carrying on. And this project, it takes space PRO as a single token and JECT as a single token. Then Gutenberg, you see how it has broken into so many tokens. To understand Gutenberg. Can you see the difference? Can you understand? Yes or no?
Yes, sir.
Yeah.
Okay. So I've shown you 3 tokenization techniques. Now let us do some comparison. So let me just do some comparison. So I will show it to you as a graph. It will be easy to understand. But here let's see the numbers first. So in character level tokenization, I had how many tokens? same as number of characters in my text. Correct. And a vocabulary size, what did it create? 100. 100 individual characters are there in the text. So it makes a compression ratio of just 1. It will always be 1 in character level tokenization because it is not compressing at all. And what is the average length of characters per token? 1. Every token has got 1 character. Right. But in white space tokenizer, I reduce the same 5 million to 1.25 million number of tokens. Okay. And I create a vocabulary size of 31,000. The compression what I achieved was 4.25. And the average number of tokens per word is 4.25. Now look at the sophisticated GPT tokenizer, BP. It creates 1.6 million tokens. That is more than white space tokenizer. The vocabulary size is also more. The compression ratio is lower than white space tokenizer. And number of tokens per word is less. So looking at these numbers, this is plotted in a chart here. Looking at these numbers, supposing I'm making an LLM, which LLM will be the most efficient?
The white space.
White space.
White space. Correct. Right. Now in terms of efficient, in terms of what? In terms of processing. Whether it will produce quality output or not, that is not ensured at this point of time. You must be clear about that. Correct? Yes, Sandeep.
So, Partha, I mean, we have done this on Shakespeare work, and let's say if we take something else.
Okay, good. I was aware of this, so I also created another one. This is on Alice in Wonderland. Okay, that book. So let me run this experiment for you before your question. I'm preempting you.
Okay.
You notice this. This has got 167 or 168,000 characters. It's only one book. The Shakespeare's work was complete Shakespeare's work. So here tokenization, you understand now. You see here, this is the tokenizer character level, and here you see word level. Okay, this must be familiar with you right now. Now notice here, noticeably Alice says, it is now broken this up into 3 tokens. Alice, apostrophe, and S. In the word level tokenizer, it is broken into 3 tokens. Okay. Now let's see Byte-Pair. Byte-Pair, it is doing it like this. It is taken the space project, space Gutenberg, space ebook, and Alice says again it is broken into 2 tokens here instead of 3, Alice and apostrophe S. Yes, Sandeep, your question now. Okay. Aditi?
No, I didn't lower down my hand. Sorry.
Okay.
Yeah.
Aditi, yes.
So Partha, here it is taking the space as well as the word as a token. So if that word appears, let's say, as the first letter of the of another paragraph, will it become another token then?
Yeah. Yeah.
Different
Obviously.
token, not the
Obviously.
same word.
Yes.
Okay.
Okay. Now notice the surprising thing. What is happening? So look at this chart. Is it any different from what you saw in the Shakespeare's chart?
Yeah, compression is better on GPT side.
What about the
Vocabulary size.
vocabulary?
Oh,
Look at the
vocabulary size
vocabulary.
comparison.
So large. Right. So prima facie, it looks like word tokenizer would do much better LLM than the Byte-Pair tokenizer. But we will see more experiments whether that really holds true or not. But so far you're clear about what you discussed, all of you? Any questions so far? Okay, no questions, I presume. Let's proceed. So this is what I showed you just now, right? Okay. So since we have no questions, let's proceed further. So you saw these also I showed you, like how this aliases is broken into tokens. Now, this is a typical problem. Now, you must be thinking that I'm going to only utilize LLM for purpose of writing text, but that is not the case, right? We also write programs. And programs, we have a major problem. That is, let's say, for example, Python program. Python program requires mandatory indentation. So indentation means I will have space continuously in many lines. So if I go by the byte-pair encoding, it will consider all different number of spaces as a different number of tokens. Major problem. Now, this was a severe limitation in ChatGPT. Now, they have made a fix, and we are yet to see whether it's really good or not, but they have made a fix for that. The major problem is that this white space removal algorithm in ChatGPT or GPT is a hard-coded stuff. So the pattern, what they utilize for recognizing white space is hard-coded. That is a major bottleneck for GPT's architecture. Now this has been to quite some extent resolved by the GitHub's architecture, which we will discuss later on. Okay. Okay. Now, oh, sorry. So I've discussed this also, how exactly the tokens get formed. So any questions on this so far? Can I just quickly go through and ask me any questions if you have?
Not for now, from my side.
Okay. Since others are silent, I guess you have no problems. Okay. Now what the LLMs do is that they have a architecture in which they fix the maximum number of tokens what they will keep in the vocabulary. Now, the motivation, I already told you that what gets fed into the neural network and what comes out of the neural network, this determines the speed and efficiency of the LLM. So that is why what they've done is that they have fixed number of tokens what they will store in their vocabulary. That's a hyperparameter which they continuously keep on adjusting to get the best results. Okay. Earlier, the standard was that the vocabulary would be 32,000. But then they increased the vocabulary to 50,000. But now we have models in which we have vocabulary of 256,000 also. So, but there's severe trade-off by adjusting this hyperparameter. So now what happens is that I discussed with you about byte-pair encoding. So you understand byte-pair encoding, but this is not very efficient in all cases. Google, this is used by Google. Google uses a tokenization system called WordPiece. So in WordPiece, what happens is that supposing I have the word like low appearing, 10,000 times in a corpus. But I have a word like Q appearing only 50 times. What this WordPiece will do is that it will not only check the consecutive bytes, how frequently they are occurring, it will also check whether the bytes appear in any other combinations also. Like, let's say LE also is there in the corpus, LA is also there in the corpus, right? It will check all these combinations. After checking all these combinations in the corpus, it may notice that the tokens, the characters Q and E are almost appearing together in 90% of the cases, right? So if it finds that Q and E appears in the tokens, in the words very frequently, then it will mark this as a token versus marking this as a token. Could you follow?
So,
Yeah, go ahead.
so Partha sir, yeah, Megha here. So what you are saying is LO might have appeared more, but sorry, did I understand correctly? So LO has appeared more than QU, or whenever Q has appeared, it always as a U. That is why QU is
No,
token based and not
LO
LO.
has definitely appeared more number of times in this particular corpus, but if he searches the entire corpus, he finds that LO is not the only combination which goes with L. There's also combinations with E, there's also combinations with A, there's also combination with I possibly, but Q it will take a probabilistic approach here, right? Q appearing with U is about 90 to 95% probable. Okay.
Yeah, got it.
So then it will mark this as a token, and whatever comes after this, if it forms a token, it will mark it with a hash prefix saying that UE is something which follows this primary token, and this is a subsequent token. So that is the difference in the word piece algorithm. Did you all follow? Any questions? Yes, Sandeep.
So Partha, can't we extend this to like in our, let's say, WhatsApp, there is this word predictor. You take it further, let's say frequency is low. So maybe that's not the right example. What comes next also you can store. 90% of the time something follows that word. So you can store that also to make it more intelligent. Am I correct?
Yes.
Okay.
It can do that.
Okay. And it will be word piece, or it is, let's say, a separate?
No, I do not know what, because it's WhatsApp. WhatsApp means it will not follow either word piece or BPE. It will follow sentence piece, because sentence piece is made by Facebook. It is used in Llama. Okay.
Okay.
Now what sentence piece does is that it removes the white space problem. What it does is it will take the complete corpus. Let's say this is a test. Supposing this is the corpus. You saw that white piece and word piece, they are considering space, right? And what it will do is that it will replace all the spaces with a underscore character. After having done this modification, then it will approach the same as byte-pair encoding and try to find tokens. Okay. Now, because of this approach, the sentence piece algorithm is very efficient, not only in English language, but in any other language where space is not a delimiter. For example, Japanese, Chinese, where space is not a delimiter. So this becomes very efficient in those languages apart from English language also. Okay, makes sense? Any questions? Yes, Yogita? Just 1
Sir,
minute.
if Google is using word piece and Llama is using sentence piece, how come they both are not using the same concept? First of all, and why would they choose different logics at all?
Yeah, because why they will choose different logics is simple. Because each algorithm has got its own pros and cons. Now, in word piece, for example, the number of tokens produced is less than BP, one advantage. Second, in sentence piece, in sentence piece, this algorithm is able to handle multiple languages equally efficiently, which word piece and BP cannot do. Okay. What does it mean for a manager? If you are looking, for example, if your work is like this, you take a report you produce in English and then you want to translate this report to Japanese and circulate to your counterpart in Japan. Right? This is your requirement. You want to use LLM. Which LLM you will utilize? You tell me.
Now we know to go with Llama, but because it is internal information, it is not easily available to us. How would we know with whom to go with?
That is why you're joining today's class.
Yes.
Correct? Now, do you get a motivation for understanding this topic?
Yes, sir.
Yeah, Ravi, please tell me.
Okay, quick question. So we do have LLM configurations for each LLM where we configure to drive our applications. In that configuration, we supposed to have temperature control. So when we try to increase the temperature of LLM configuration, it is going to produce more intelligent output. That is what actually LLM configuration indicates that one. When we increase that one, how does it is going to show impact on the consumption of the tokens?
Ravi, I will come to the temperature part in detail. Give it some few sessions. I have to first of all take you to the beginning of the neural network, and the beginning of the neural network is the word embeddings. So let's go step by step. So give me a little number of sessions. I will come to your question.
Sure. Thank you so much. Yeah.
Yes, Sandeep.
So, Partha, sir, so now we know these algorithms, but from a company perspective, I don't know commercially, is it possible to segregate for my reporting section to let's say other countries? I use this, but if I have something else, then I use BERT, and then for something else, Llama.
Very good question and a very important question. In fact, you should read my article in this regard. I will see if I can give you that to you. Just 1 minute.
Put the link then. Yeah.
I will give you the article which I wrote in this regard. Architecture, not this.
And maybe while you are looking at it, so I am from payments domain, and we have a concept called as orchestration layer, where it looks for the best possible route to process a payment. Okay. If it's a cross-border payment, then the best possible FX, cost, etc. So are we heading in that direction that dynamically it might choose the best LLM? Do you think?
No, that is not the way to go forward.
Okay.
I'm just trying to look for the right article for you. I wrote an article on this very recently, where I explain how you should choose LLM. Just 1 minute, guys. Just hold on. No, not this. I will give you the right answer. I gave a precise answer to this question. This is the one. So I'm giving this link to you guys on the chat. You can read this article. I will explain anyway what I'm trying to say. The thing is that as a executive, how do you decide your AI journey? What is happening is that organizations say that AI is very useful, so let me make the AI tools available to everyone. A typical example, which I've heard many number of times, whenever I've had any session or any discussion, is that many managers have told me that we gave Copilot to everyone and our productivity increased. Is that the right way? You should ask yourself. I think that is not the right way. Because it is not enough to give a tool. It is what is required is to give a tool to a part of the organization which it requires that specific tool the most. A simple example in the context of our discussion today, supposing you are making a choice that I will make LLMs available to my team in the company. Then, when it comes to your American part of this company or the European part, maybe not even Europe, maybe American part and British part, you should consider giving them OpenAI ChatGPT. When it comes to the eastern part, the Chinese or Japanese or Korean, then you should consider giving them Llama. If it comes to the European part, then possibly you should give them Gemini. That way, you should understand which is the power of, which is the strength of which LLM, and based on the strength, should find where that LLM finds the best use case. Only then you will have maximum return on your investment. Does it make sense to you guys?
It makes sense, but just maybe a raw statement on that. The more vendors I have generally in an organization, I mean, it's from a procurement and manage. I don't know how easy it is to get off of one LLM if I start building something on that, right? So coming from my enterprise world, the more integration points you have, futuristically, the more maintenance support it is. So I don't know in this context how easy or
from an architectural point of view. See, I was an enterprise architect and I had this question. I had this dilemma many times.
Yeah.
Should I go for small number of vendors or should I go for large number of vendors? Now, the problem with small number of vendors is that I can get logged in, and then I can be taken for a ride based on their whims and fancies, right? If I have small number of vendors. On the other hand, if I have large number of vendors, then I can be in for endless amount of integration issues throughout my life.
Yeah.
So this is a dilemma which any enterprise architect always has. However, so this dilemma is a trade-off. So you have to balance where is the right point in terms of number of vendors and a number of in terms of number of vendors. Basically, the thing where I have the minimum lock-in possibilities and minimum integration issues possibilities. Right?
Okay. Yeah. Okay.
That's an architectural decision.
Okay. Thank you.
Yes, Megha.
Partha, sir, any specific reason for saying Gemini for Europe and OpenAI ChatGPT for Americas?
The ChatGPT is very efficient on English language, right?
Mm-hmm.
You saw the architecture, the tokenization mechanism. Tokenization is the input to LLM, right? Now that input is very vital. You must have understood by now that is very vital. This will become more clear as we carry on the discussions. But so it is very, the way it is designed, the byte-pair encoding technique, it works on any language, but it is very inefficient on non-English languages. Like supposing you have English text of 1,000 words. Now in byte-pair encoding, I might have a situation, the worst case could be I will have around about 1,300 tokens out of these 1,000 words in byte-pair encoding if it is English language. The same 1,000 characters of Japanese, 1,000 words of Japanese language in byte-pair encoding can result in 3,000 to 4,000 tokens. You see the inefficiency what is getting built in.
Mm-hmm. Okay, got it.
Okay. Yes, Jatinder Singh.
Related to adoption of the LLM, I have a different experience. Like I saw there's a light LLM solution where it automatically have a mode where we can select automatically which LLM can do the best. Otherwise, anyone can pick like which LLM need to use. I have like this type of experience instead of adopting like based on the geographical things.
Okay. Thanks for sharing. Yeah.
So building upon that, Partha, so right now we see, let's say in Claude or some other, you can choose the model in the drop down, right? Is that the same thing which he just mentioned? Like dynamically you can choose?
Yeah. But dynamically you can choose model. That every system gives you that possibility. Right? Now, you check any system, it will give you that possibility. But then I am coming today to all of you from the ground level of every different LLM. Right? Every model of ChatGPT has got many models. Light model, O dash models, and then what do you call ChatGPT 5.4 and all kind of stuff. They are different for different purposes. But then they are the base level where the model building starts. Tokenization. All OpenAI's models use the same BPE.
Okay, got it.
Okay. Okay, so let's move forward. Now, what they did an experiment in Harvard and MIT and produced a algorithm called PathPiece. Now, PathPiece was an algorithm in which, PathPiece was an algorithm which produces the minimum number of tokens and that produces the maximum compression of any corpus. But they found that by doing the minimization of number of tokens or achieving the maximum compression, the LLM loses its comprehensibility of the language. Okay, this chart is showing that what is the experiment's result, what they found. Compression is very high, very efficient, but then it doesn't semantically understand the language. That is why you never find any company using this technology called PathPiece. Okay. Now this is something you can experiment. Supposing I experimented this. Supposing you take GPT-3 for example, if it is still available in your machines, and try to count the number of R's in strawberry. In most circumstances, not only most circumstances, GPT-3 will always give you the wrong answer. That is because it breaks down into tokens and then it counts R's within the tokens and it gets it all wrong. So this is another problem if you have the wrong kind of tokenization technique. Okay. Now in GPT-5, it does not make this problem. It will tell you correctly. So another problem which we have is in ChatGPT, it many times mixes up calculations because it finds a number like 677 and breaks it up into 6 and 77. Because of this, it messes up with calculations. Right. Now, you will not find such problems with Llama because of their tokenization strategy. So these are all some hidden flaws. Now, the problem is that you must be aware of these things. And another reason why you should always check the output produced by your LLMs. Because inherently, how it is working internally, because of that, it can produce number of errors. So you should never take the output of an LLM without having checked it thoroughly. Okay. Okay. I already discussed this with you. That is, when it comes to unfamiliar languages, it creates many tokens because it doesn't understand. This is taken care to a large extent by sentence piece algorithm of Llama, more efficient for non-English languages. Now, generally, the English language, it produces about 4 characters per token, and other languages is much more fragmented. So when you're considering a LLM for non-English languages, better not to consider ChatGPT. That is my advice. Because fragmentation means that you will have more number of tokens. More number of tokens means higher amount of processing requirement. Higher processing requirements means you will be charged more. And also, the output what it will produce will be less reliable. Any questions or any comments on this?
Partha sir, just curious to know about Hindi. So is Hindi similar to English, or is ChatGPT good at that?
No. ChatGPT is not good.
Okay. I mean, nowadays I see those ads, right, where it answers in English and Hindi mix. So I was just wondering.
They do ads, and ChatGPT can talk in 50 languages. But being able to talk in 50 languages doesn't mean it is good in all the languages.
Mm-hmm.
See, there are two things. One, it may be good also. It may do the necessary things on a basic level. But will that doing result in optimized cost for you is also a question you must ask.
Right.
Right. If its understanding of a language is not very good, it will utilize more tokens.
Mm-hmm.
More number of tokens it utilizes, more is the cost to you.
Right.
Okay. Now let's look at what we are looking going forward. Going forward, now scientists are experimenting with something called as Super BP. Super BP is, I will take regular phrases like by the way, and I will create a single token out of it, which is known as the super word. So if I can create tokens like this, then will the number of tokens required by me not reduce? What do you guys have a first impression? Will the number of tokens reduce or not?
Yes.
I think it will reduce.
It will reduce drastically. It will reduce. Okay. So this is the new direction what scientists are exploring. And another thing which is under pipeline, which is getting explored, is that how do I completely take out the vocabulary stuff itself? This word embedding layer, which I will discuss in the next class. How do I take it out altogether? So that is the next frontier where we're doing byte level transformers, where I take my raw bytes and feed them directly into an encoder. So I will not discuss this further today, just coining these words for you so that you are prepared when we start discussing about embedding and transformers and ultimately attention mechanism and then LLM architecture in full. So, yeah.
Sorry. So in the previous frontiers, you talked about super BPE. So when, as part of the super BPE, when by the way word is considered as one token, does that mean that by the way as a separate tokens are removed from the vocabulary list?
Could be or could be not also.
So then how does we say that has yield a fewer token?
No,
what is the strategy here?
Supposing you have a input in which you have utilized by the way many times, and supposing you may or may not have used the by, the, and way separately in your text, right? In that case, supposing you are using BPE, standard BPE, will number of tokens not be more as compared to super BPE?
Okay, so but the vocabulary will still remain. It will be more than the previous one, but the number of tokens that we have as an input that is going to the model and coming out will be less. That's what the understanding, right?
Yes.
Okay.
Yes.
So which means that this increases the size of the model also, because we are adding more vocabulary to the list.
Yeah. Definitely.
Okay. Understood. Thank you.
Okay. So I will discuss subsequently about this transformers and everything, and then it will become more clear how we can get rid of this embedding and move directly to the transformer. But this is something which is work in progress. It is not a reality still. So this is the future which we are looking at. Any questions? Yes, Sandeep.
Sir, different question. Did you make these slides yourself?
No, these slides are entirely made by LLM.
Which one, if you don't mind sharing?
Notebook LLM.
Okay, they're very nice.
Yeah. Since it's a session on LLM, I created all the slides using LLM. In fact, even the last slide, okay, I've discussed all these things with you. Now, here's the appeal. This slide also is made using Notebook LM based on a prompt I generated. The thing is that I fund all my research, so it requires money. So in case you feel the sessions are useful, you can contribute a small amounts according to your capability and desire, so that I can support my research and move forward. I'm too shy. Actually, I could not have done it in the past, but I think I should break this shyness and try to fund myself. Okay. Anyway, that's something. I hope the session was useful to you guys. So I will share this slide deck with you as well. I will share this slide deck. 1 minute. File. So that if you in the next session, if you have any questions, you can ask, or if you feel it's useful to go through this, you can go through this. Yeah. So you can download it. I will give you some time for that. So any other question before we close today's session? I give you some time to download the slide deck. So
where is the link for the? Oh, okay, thank you.
Link for what?
Yeah. Okay, I got it, sir.
Yeah.
One quick question, sir.
Yeah.
Is there any follow-up reads or any book that will help us reinforce the learning better?
So good question. I will suggest a book to you next class. Today I'm not prepared with that answer.
Okay.
Yeah, I should have considered that, and I will fill this void the next class.
Okay.
Partha, will the recording be available for this?
Yeah. This is automatically getting recorded. So I will process it and I'll post it on LinkedIn.
Okay, thanks.
This slide deck, this otter.ai, is that it?
Which one?
Slide deck is at otter.ai.
No, notebook LM. That is a tool I
okay.
utilized.
Okay. There is some link in the chat, otter.ai full summary. Okay.
Yeah, I think that is for the transcript.
Okay.
Somebody
where do I-
enabled it, yeah.
Where do you download that site? Oh, okay. Thank you.
Okay.
So as a general voice bot, was the session useful to you guys?
Yes, sir.
Yes, sir.
Definitely, it was
Yes,
very
yes.
detailed.
Very useful.
Yeah.
Pretty
Yes,
useful.
sir.
Okay, thank you. That is a token. Good enough for me.